Hello, chemists. Me again. Let's finish out that radical information. So I'm going to go back to the handout. And the last thing we really need to talk about as far as new reactions is something called polymerization. And then there'll be a little bit on, where do radicals occur in our lives? All right, so let's talk about polymerization. There's going to be two types of polymerization, addition versus condensation. And condensation is exactly like it means. Usually condensation means the loss of water, but in this case, it can mean the loss of a small molecule. But addition is often called the chain growth polymer. And it's going to just keep adding, adding, adding. This is probably the one that most people think of when you think of radical polymerization. All right, how do you get it started? Generally, you have to have some kind of a Lewis acid or base. And of course, just like we had for all of our radical reactions, you have to have some kind of initiator. Here's the kicker. The monomers must contain pi bonds. That's the key to these ones. The rapid addition of one molecule at a time. Okay, so it's put one on, put one on, put one on. And then the growing end actually has an intermediate. Generally, it's a radical, but it could be a cation or an anion. But generally, at least for our purposes, it's going to be a radical. They generally start with just a carbon-carbon formation, where we'll see that's different in the other type. And the monomers are added so that the product contains a multiple. So when you see this, it is containing a multiple of the monomer units. And because it's a multiple of the monomer units, the empirical formula is pretty much identical to that of the original monomer. And as we continue in the reaction, the concentration of that monomer will decrease and there are no byproducts. So let's take a look at a chain growth polymer. Let's see, we'll be really generic. We'll just take this one. Now, of course, the key is we have to start our reaction. So I'm going to take my hydrogen peroxide and it is going to do the first radical formation. And then, okay, let's go to the radical. Question number 1. Why did the radical go here instead of here? This is a primary with no help. This is a secondary with help, so it is the more stable radical. And now, what is going to happen? Oh, whoops, I forgot to draw my OR. Okay, and that's attached. So we now have, changing colors, we now have the growing end. And of course I write too big, so we're going to go to the whiteboard. All right, so let's take a look in detail. All right, so the first step, oh, you know what, let's just do the overall product. All right, so there's a generic product of this particular one. And we want to point out, let's see, my monomer units. And then we, of course, could write as many or just leave it with the squiggle saying that it is continual. Okay, first step. You know, I should draw that differently so it doesn't look like I'm making the bond right there. Because we know that this is the one that connects to the OR. All right, so our first intermediate All right, there's our first one. And guess what? It is now going to do the exact same. And this is the most stable radical location. So as we continue on, that is going to be the growing end. So I'm going to make a new bond right there. I'm going to make the radical. And guess what? It reacts with another one until it is stopped or the monomer runs out. Okay, so it can continually go depending on the concentrations and whether the radical conditions aren't terminated. And so we'll just make one more right here. And we're gonna 1, 2, I did 3. 1, 2, 3. Okay, so some kind of termination. The other thing that I had a question about is what in the world is this OR thing? Do all of them have this reaction, to start it? And for our purposes, yes, we're going to put the OR on the end, but know that in the very end, it is just the plain radical. All right, there is chain growth or addition. Recap. It has to have a carbon-carbon double bond. It adds different monomers together, forming carbon-carbon double bonds, not double bonds, carbon-carbon bonds. And usually it will keep going until you run out of monomer or you terminate it. There isn't a loss of a little molecule either. All right, so there's addition. Let's take a look at the other one. This one is called condensation polymerization because it's going to lose a small particle. Generally, it is a non-radical mechanism. So the only reason I threw it in this chapter is when we hear polymerization, we generally think about the radical mechanisms, and I wanted to do a compare and contrast. But these condensation ones generally are not radical reactions. The monomers must contain a substitution functional group. All right, long time ago, we talked about the powers of each one of the functional groups. And when I go to the whiteboard, I will do a review of that. But the key is it has to do some kind of a substitution. It generally grows by, oh, here's another big difference, a carbon heteroatom bond. Most of the time, carbon oxygen or carbon nitrogen. Okay. So there's technically two different types of monomers. The polymer molecular weight is not just a multiple of the monomer because we're combining two unique types together. And the empirical formula is, where are we? And the empirical formula is not the same because now we have combined two different types of molecules. The concentration of the monomer disappears very early in the reaction because we're taking two things to react at the beginning. And that usually loses some kind of a little molecule. Water gives it the name condensation. All right, well, what kind of a mechanism are we talking here? Well, if there's two types of intermediates, we have to look at them differently. So you can have a cation intermediate or you could have an anion intermediate, and we'll just kind of look at both. All right, if you want the cation, boron, such a special little molecule. If you take boron plus hydrogen peroxide, you're going to make this complex. So it's a water boron complex and it has a name, but I can never remember the name. If I draw out the Lewis structure of that, all right, there is my reactive species. There's my reactive. And so this is one of the initiators for my cation. And I'm going to have to, of course, go to the whiteboard. So let's take a look at. Okay. So again, I'm going to put the letter Z, but that means that we have to have some kind of a withdrawing group. So this doesn't necessarily have to be a carbon, but we're just being pretty generic right here. And that is going to react with, all right, I'm going to draw a little funny here, just so that you can see which one is reactive. Okay, I'm not doing a radical mechanism, but I have a pi bond and I have an excellent electrophile. And so my pi bond's going to break. It's going to go after that hydrogen and it is going to kick down. And whenever I break a pi bond, don't put two there. Anytime you put a pi bond, you put two things in its place. And in this case, we're going to put a carbocation. And so my question to you is, where should the carbocation go? The power of an electron withdrawing group is it stabilizes the formation. Oh, look, there is my starting material. And so this, remember, could be something other than a carbon, but just generically. Hey, I like positives. Okay. Boy, I write big. Let me see. I'm going to have to write the carbons. And just like we saw before, the growing end of the molecule, in this case, is a carbocation. Well, didn't you say that you have to have, some kind of maybe not carbon-carbon bond? That depends on the electron withdrawing group. So for instance, let me look if I drew myself a specific. Yes, right there. Oh, because it's on the next page. That's why I had it. So this one's going to be really generic. We're going to say, okay, we'll just do an ester. All right, well, what would we do with the ester? In this case, take our BF3 complex. Okay, what is the most likely place? Well, we still have a pi bond. Now I know this is going to look funny. I don't know why I drew that line. And we have, okay, I've broken that, and we have a carbocation right there. Well, I'm not seeing still how I'm going to put the, wow, I'm really stumbling. I apologize. How am I going to put it on this particular piece? Let me actually show you our substitution. Electron withdrawing groups. Let me see, ketone. Let's go carboxylic acid. Ester. Then we'd have amides. Then we'd have acid halides. And then we'd have anhydrides. Now, this type of substitution reaction is actually coming up in a future chapter, but let's just do a brief review of what we know. This one has a pi bond. Okay, so that's pretty much its reaction, and it's a leaving group. Okay, pi bond, and it's also a leaving group. Oh ho ho ho! Remember, carboxylic acids, they prefer acid-base chemistry first, and then they have a pi bond with a leaving group. That's not usually what carboxylic acids do. Oh, look, I have a pi bond and I have a leaving group, but I have a polar carbon-oxygen bond. That one's kind of fence sitter, and so is this one. But these two, they are made for substitution. These two generally like to break that pi bond into an addition reaction. This one likes acid-base chemistry. These are your fence sitters. They kind of go both ways. And then we've got our substitution reactions. Ew, okay. Now I'm going to have to clear the board. So that's how we're going to look at our carbonyl groups. Remember, electron withdrawing groups don't have to be carbonyls, but it's the easiest one to actually visualize. Let me see, clear. And as you can tell, this kind of chemistry isn't quite as familiar to me as the others. So I am actually peeking at specific reaction mechanisms here. All right, we're going to try this next one. Okay. There is an anion intermediate. I'm going to come back to that, but here's the specific types. What kind of carbon bond do you want to form? If it is a carbon nitrogen, the polyamides, polyesters, okay, you're making an ester. Polyurethanes is a functional group we really haven't talked about, and the polycarbonates. So those are the different types of compounds. And that's what I'm going to do right now. I'm doing the example for polyamides. All right. This fun little molecule all right, so we have this fun little, oh look, it has a carboxylic acid and an amide on it. So it has both kinds. We would react that together to make, I'm going to put this in the zigzag. So this one is R. I lied. That's why it looks funny, because there's a carbon in there. And you're thinking, wow, Jolly, hope you're not a polymer chemist. Yep, not really my thing. Oh yeah, there's my NH2. So there's that one. There's my R group. There's my carbonyl. There's my OH. All right, the key is, aha, there it is. There is my amide bond. And that amide bond then goes up to the R group, goes down to an N group, goes up to a carboxylic acid. All right, and it keeps going and going. So here is pretty much the addition. That's the polymer. And wait, you say, where did my other piece go? If you'll notice, I'm losing the components of water. This carbonyl right here, remember, it had one of those and a hydrogen and a hydrogen. So those two will combine and lose water. I don't know. That doesn't feel like we talked about that really good. Let's see if we can actually walk through a very specific mechanism. Now I'll draw it kind of funny. Ah. All right. Nitrogens are more basic than the carboxylic acids, but this is the component we're going to lose. So, who's the nitrogen actually going to attack? Okay. This is a carboxylic acid, and the hydrogen be ripped out first, but that wouldn't show me my fun little mechanism. And in a concerted looking mechanism. All right, once those two are attached, the OH will attach to this, and that is now a good leaving group, and it will leave. Now, how detailed are we going to be in our mechanism? Not. As long as you can see the starting material and you can see the ending polymer, you don't have to do the complete mechanism like this. Now, the radical mechanism, that's part of the chapter, and that one's important. This, as long as you can see the two pieces. And then what came off right here is the water. All right, so there is a generic substitution. Okay. So that's condensation polymerization. What kind of condensation polymerization are there? Well, now we get to talk about the functional groups. So the polyamide is the one that I actually just did. Okay, those are basically wool and silk, synthetic nylons, the aramids. Okay, there's all sorts of them, but the key is they have an amide bond, and I think the two most interesting are wool and silk. All right. Polyesters, they use a molecule called polyethylene yeah, say this, terphthalate. And that funky molecule looks like this. Whoa, it has two growing sides. So if you were going to make its, oh, room. If you're going to make its polymer, and then you would go on, you would form an ester bond. All right, the polyurethanes, I didn't even know what the structure of polyurethane was before I started seeing these types of polymers. And so I am peeking. Whoa, stop. A polyurethane looks like this. O double bond to a C, which is double bonded to a nitrogen. I know that looks funny to us. Which is bonded to some kind of R group, which is bonded again to an N, which is bonded to a C, which is bonded to an O, and then you always react that with a diol. And that gives you your polyurethanes. Again, are you going to have to know these structures? No, but it's nice to know the different types. Okay, now polycarbonates, and I know you've heard this term before. That is a carbonate. It's a CO3, but it's connecting them together. This one, they're very strong, very tough, but also easily worked with. And so the place that I always knew them is in lenses. So if you wear glasses, hey, it's a polycarbonate lens, blah, 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 because they're stronger, they're clear. Yeah, okay. You can get opaque and transparent. I know I wrote that kind of funny. So you can get them in clear or transparent, or you could get them in opaque. All right, another one is an epoxy resin, and boy, do those have the weirdest shape. Epoxide. That is exactly what it has. Let's see. Usually that's a carbon. Oh, I put the oxygen on the wrong side. Obviously, I don't play with polymers. Again, I just wanted you to see some of the structures we're starting with. You know what? I'll do that. Get them out of the way. And here's the funky epoxide. And it happens over here too. That is an epoxy. Usually these are the sticky ones where you use them for adhesives. And the reason I put a polyether in here is because this is what makes up those building bricks. Okay, one of the original formulas. And we'll just stop right there. All right, again, do we have to know all those different types? No, but we do need to know that addition puts on carbon-carbon bonds using radical, and condensation actually does a reaction not with a radical, and it usually makes a carbon heteroatom bond. And let's see if I can blow this up or not. You know what? I could go up there and blow it up, but I'm not going to mess with it. Here are a whole bunch of different types that I thought you would be familiar with. They would kind of ring a bell. I am going to blow it up. All right. Polyethylene. Okay. There's the key. It's giving you your starting material. So this are addition polymers. So if you'll notice that has a pi bond. This one, same molecule with an attachment. Oh, just a different attachment. Oh, look, just different attachments. And so the key to those addition polymers is you're just putting attachments onto the carbon-carbon double bond. And so this one's PVC, this one's polystyrene, this one's Teflon, which is polytetrafluoroethene. And here's some common condensation ones. And it doesn't look like I put it here, but I got those off the web at the bottom. I put the reference. All right. One of my favorites is nylon. Now, there are different forms of nylon, but there's that funky molecule that I drew for you. And the key here, oh, look, I have an amide bond. And then these others probably aren't going to be as familiar to you, except for the polyesters. Again, you can get a lot of information from its name. Ultimately, do you have to know the difference? Like if you were to look at a polymer and say, oh, is that an addition or is that a condensation? Hopefully you can tell because condensation has heteroatom bonds. And here's the fun part for this semester because we're going to eventually end up with biochemistry, some naturally occurring polymers. Woohoo! Polysaccharides. We have a whole chapter on carbohydrates, and I'm going to teach you how to build those saccharides, and I'm going to allude to this very moment. Hey, do you remember when we were doing condensation polymers? We're doing that right now, which is basically what nature does to make your polysaccharides. It has a very special type of bond called an acetal linkage. Again, we'll talk about that during the carbohydrate, but I just wanted you to take a look here. All right, so cellulose, okay, its monomer is something called beta glucose, and it doesn't branch. So you get this wonderful linear relationship. Now, starch, on the other hand, little stereochemistry action here, alpha versus beta, and it has about 4 linked together, but amylopectin then branches. So we have these linears and then we have these branches. And so I love this picture just because of those two in that diagram. And then glycogen, our storage of carbohydrates, again, is using our wonderful alpha. And again, branches, but look at that branching. And this is a lot of the bio stuff that we do at the end of the semester. I just figured you'd be familiar with it and it would be interesting to see what kind of shapes. So again, oh, there's the reference. Here, just again, for interest, you can have natural polymers or you could have bio-based polymers. Aha, here is the end of our semester. We are going to talk about those lipids. We're going to talk about proteins. We're going to talk about the sugars and the carbohydrates. Hey, guess what? The synthesized ones, yeah, we're not going to touch so much. But don't forget, they are designed in lots of places, the bacterial. Okay, now notice I said from biomass. These are also produced in nature. But those are the three that we're going to talk about at the end of the semester. And then I thought this was actually a nice thing. I printed one of these for me because it kind of just breaks it down. Is it based on the backbone or is it based on the origin? Okay, blah, blah, blah. It was just a nice list that I thought you'd like. All right, question number 6. For each of the following, show at least 3 monomer additions. Now, if it's the radical, I would suggest you do the actual mechanism. If it is not the radical, if it is the condensation, just show me where it does attach. Question 7. For each of the following, identify the monomer. So in the previous question, you were putting it together, and in this question, I want you to see it broken down. So let's take a look. Ooh, there's a nitrogen and there's a nitrogen. So that looks like a natural spot right there. Okay, so that's how you would do that. I don't give you very many problems, so I won't do yours. All right. And that ends the discussion for addition versus condensation polymers. We'll do a basic characteristics and some naturally occurring ones here in just a minute. All right, until next time, jolly out.